All right, this chapter is the Doppler effect. We'll get into it. Uh, it's actually pretty easy stuff. We can sum it up by saying that the received frequency response, delta F, is directly proportional to the transmitted frequency, F sub 0, and the transmission receive angle. Therefore, the unconverted frequency shift estimates delta F will degrade as a function of the cosine of the angle which the transmitted beam is displaced to the line of insulated beam. Yeah, this is why we hate Doppler physics. It looks like a bunch of stuff that's difficult to understand, a foreign language, but if we go through this one step at a time, we're actually going to understand it quite easily. So let's start out with the Doppler shift. The Doppler shift is also called the Doppler frequency. This is the difference between the transmitted frequency and the received frequency. A Doppler shift occurs whenever a sound source and receiver move closer together or farther apart. Anytime they are the same distance apart, even instantaneously, you're not going to have a change in the frequency shift. Okay, so if you're in front of a source that's moving, you're going to notice an increase in the frequency or a decrease in the wavelength. And if you're behind a source that's moving away from you, you're going to notice a decrease in the frequency or an increase in the wavelength. We use this principle to measure the velocity of the blood in the human body, and that will tell us, by understanding something about hemodynamics, that will tell us something about the disease process that's going on. So Doppler shift in ultrasound is much lower than our transmitted frequency. If we send out sound at between 2 to 20 megahertz, our Doppler shifts are going to be around 20 to 10,000, well, actually even less than that, 4,000 hertz, okay, 3 to 4,000 hertz. So Doppler is far, far less than our ultrasound frequency, and it's kind of unique in that the Doppler shift is in the range of human hearing. So if you see this Doppler shift of 3,000 hertz here, well, that's certainly within the range of human hearing. There is an easy way to calculate the Doppler shift, and that's just simply the reflected frequency, the received frequency, minus the transmitted frequency. That's the easy way to measure it, and it gives us very little information. So we're going to learn other ways to measure it that give us more information. Doppler shifts are created whenever the sound strikes moving red blood cells. By the way, this echo off of moving red blood cells is Rayleigh scattering, and Rayleigh scattering, if you remember, occurs increases with the fourth power of the frequency. So if we double our frequency, we're going to get 16 times more reflection off of blood cells. So anyhow, Doppler shifts are created when the sound strikes moving red blood cells. A positive shift occurs when blood is moving towards the transducer. This means that the reflected frequency is higher than the transmitted frequency. Normally, we display that above the baseline, where the baseline is here, it represents zero velocity, and anything above it up here represents flow that is moving towards the transducer. Anything below the baseline, like down here, is flow moving away from the transducer. So normally, positive shifts are shown above the transducer. There's exceptions, but that's the normal. Negative shifts occur when blood is moving away from the transducer. In this case, the reflected frequency is lower than the transmitted frequency, and we often will display those below the baseline. So if your received frequency is higher than your transmitted frequency, the blood is moving towards you. If your received frequency is lower than the transmitted frequency, the blood is moving away from you. So we can use that to determine Doppler direction. With Doppler direction, if we don't invert our flow, then flow above the baseline is demonstrated as above the is going up, and flow below the baseline is demonstrated as going below the base, flow away from the transducer is going down below the baseline. So let me repeat that. Flow towards the transducer, so flow coming in and going towards the transducer is going to be projected going up above the baseline, and flow away from the transducer, in this case over here, is going to be projected going down below the baseline. And when we talk about the position of the transducer, we're actually talking about where on the transducer the incination line for the Doppler is actually at. Okay, so even though you may have a wide transducer here, we're only using the left side here when we're insonating in this section on the right side of the vessel. So this is coming towards this transducer if it's flowing this way. In this case, the arrow shows the blood flowing away. So this would be away from this point of the transducer and toward this point of the transducer. Speed tells us how fast the blood is moving in the body. That's useful. But velocity tells us not only how fast the blood is moving, but what direction it's also going. So we have to know the velocity of the blood. We don't need to know just the speed. We have to know the velocity of the blood. Now let's discuss the Doppler equation. Okay. What the heck is that thing? Well, the Doppler equation just simply tells us that the Doppler shift is twice, because this is round trip effect, the original frequency times the velocity of the blood times the cosine of the angle difference between the blood flow and the transducer incination angle divided by the speed of sound. So when we look at that, frequency shift, the Doppler shift, is due to the round trip effect. Okay, the round trip effect is never going to change, so that's always going to be there. The transmit frequency times the transmit frequency, well, we can certainly adjust the transmit frequency. We have a button on our machine for that. Times the speed of the blood, well, we can't do anything about the speed of the blood because that's set. Times the cosine of the angle between the ultrasound beam and the blood flow. So, and then divided by C, which is the speed of sound in the body. So what this tells us in a nutshell is that the Doppler shift is related to two things we can control: the incination frequency and the angle of incination. Everything else is fixed, so we can't do anything about it. We can control the angle that we incinate the blood at, and we can control the frequency. Everything else we can't change, and so we got to learn to live with it. So if you want to adjust your Doppler frequency, those are the two things you can adjust: your incination angle and your speed, or your frequency of your transmitted pulse. So the Doppler equation gives us a relationship between the blood flow and the Doppler shift. The faster the blood flow, the greater the Doppler shift. If the blood velocity doubles, then the Doppler shift doubles. if the blood velocity halves, the Doppler shift halves. And remember, we don't control the blood velocity. That's up to the patient. So we're just measuring it. The relationship between the transmit frequency and the Doppler shift, the higher the frequency, the greater the Doppler shift. If you double the frequency, you double your Doppler shift. It's that simple. If you half the frequency, you half the Doppler shift. And so lastly, then, when we look at it, we look at the relationship between the transmit frequency and the Doppler angle. If we have no angle, if we're insonating parallel to the blood, then the angle is 0 and the cosine of the angle, cosine of 0, is 1. When we're at 90 degrees to the flow, the cosine of the angle is 0, therefore we get no Doppler shift. If you put a 0 in for your cosine of your angle, you're going to get 0 for your Doppler shift. When the angle is 60, the cosine is 0.5. And we never take Doppler measurements with any angle greater than 60. So from 60 to 90, we never take a measurement. Mathematically, our maximum Doppler shift is always going to be with an angle of 0. So the Doppler equation and the velocity equations. Well, what we're really interested in is not the Doppler shift. Remember, we can get that by just subtracting the received frequency, the transmitted frequency, from the received frequency. That's the Doppler shift. What we're really interested in is the velocity of the blood, because that gives us diagnostic information that we can utilize to help our patients. So the velocity of the blood is gotten by taking our Doppler equation, solving for V, and we end up with the Doppler shift times the speed of sound divided by twice the transmitted frequency times the cosine of the angle. So that gives us our velocity, and that gives us diagnostic information. When we look at a scale, oftentimes we'll have scales that give us both the frequency shift in kilohertz and the velocity in centimeters per second. So the frequency shift, again, is just the frequency received minus the transmitted frequency. The velocity is when we take that Doppler shift and we multiply it by the speed of sound, divide by 2, divide by the transmit frequency, and divide by the cosine of the angle. And our angle is here given as angle correction of 60 degrees in this case. So why go to all this trouble? Well, frequency shifts aren't clinically meaningful. We said that. The velocity of the blood is very relevant. So we need to be able to solve for that velocity. So the sound beam direction and flow direction. When the beam is parallel to the flow, the entire frequency shift would be obtained. At any other angle, so any angle greater than 0, the frequency shift is diminished due to that angle, the cosine of that angle. The percent diminution is calculated by the cosine. The angle is the direction of insonation to the direction of blood flow. And at 90 degrees, there is no frequency shift. But again, we never measure Doppler shifts above 60. So here's an example of blood flow going from right to left, because red is above the baseline and it's coming, and so red must be going towards the transducer, so up towards the transducer. And so it's going from right to left. And if we take a measurement of that, we see that our velocity is about 66 centimeters per second with a Doppler shift of about 1.5 kilohertz, just under 1.5 kilohertz. If we increase the angle, or decrease the angle, excuse me, so in the previous we had an angle of 60, angle of 60. If we decrease the angle to 50, we see the Doppler shift goes up over 1.75, but the velocity is now reading out only 64, so minimal change in the velocity. Let's go back 66. Here within the region of error, it's 64, so it's still within our error. Now, if we decrease our angle to 45 degrees, you can see that the Doppler shift is now reaching 2.5 kilohertz for the most part. And because we're utilizing the angle of 45 degrees and we're measuring the velocity, our velocity is relatively the same. So here we had 64, previously 66. Now we're still at 70. So even though we have differences in angles that we're looking at this blood flow, we're getting essentially the same measurement in velocity. That's called standardization, and that's what was standardized across labs years ago. Okay, I got to take a break here. Hang on. It's time for office hours. So we see that changing the Doppler angle changes the Doppler shift, the frequency shift, but really doesn't affect the velocity. Okay, and that was the standardization that labs made. Before this, labs would utilize blind scanning probes or continuous wave probes. Everyone had no idea exactly what angle they were at, and so you had to use just the frequency shift to determine whether or not something was a diseased vessel. And so by doing that, when they did that, it was very difficult to be consistent from lab to lab. Now we have utilized this ability to see the anatomy and put an angle in it, and this has made our velocity measurements possible. And so if you get a carotid done at one lab, it should be very similar to one done at another lab. And that's been the main goal of Doppler angle correction. So let's look at the Doppler shift and the cosine. So as I said, mathematically, the Doppler shift is directly related to the cosine of theta, where theta is the angle between the inclination line and the blood flow direction. If the cosine is reduced by half, then the Doppler shift is reduced by half. And also your sensitivity to Doppler signal is reduced by half, right? I hope that makes sense. So at 60 degrees, which most people use, the frequency shift is exactly half of its maximum. When we use a Doppler angle of 0, it means we're getting the full cosine. And if we use a Doppler angle of 180, we'd be getting the same, it's the same thing as 0, but just from another direction. So this chart shows you the Doppler, the cosines from 0 to 180 degrees. And in practice, we only go up to 90 degrees with our machines because after 90 degrees, we just start going back down to 0 in the opposite direction. The idea that we can have direction in our Doppler shift, it was created by something called the phase quadrature detector. And so this gives us our bidirectional Doppler. It gives us positive and negative shifts. It tells us that it's either above or below the baseline. If you listen to the Doppler shift coming out of the speakers on the machine, if it's above the baseline, it'll be coming out of one speaker, and if it's below the baseline, it'll be coming out of the other one. What they're doing is they're taking literally the Doppler shift and they're sending it directly to the speakers. And if they send it to the right speaker, let's say, it's positive. If they send it to the left speaker, then it's a negative Doppler shift and it's below the baseline. Visually, we see this as flow either above or below the baseline in our spectral display. The flow in the other direction would be going on the opposite side of the baseline, our spectral display. So you can determine by looking at your image whether or not the flow is going toward or away from you. And the part of the system, as I said, that determines this is called the quadrature phase detector, phase quadrature detector. And what you need to know is that there's something called a phase quadrature detector, and it determines the direction of flow. So what determines the direction of flow in an ultrasound machine? The phase quadrature detector. How does it work? It's magic. Let's talk about continuous wave ultrasound briefly. We've mentioned continuous wave ultrasound and such things as intensities, and talking about how duty factor with continuous wave is always 100%. The way this works is that there's two crystals that are used in the continuous wave transducer, and one is constantly transmitting a signal. So there's no pulse, it's just a constant wave. The other one is constantly receiving a signal. Now, this has the advantage that we can detect very high velocity shifts with it, and we'll never get aliasing because there's no pulse. So we haven't talked about aliasing yet, but there's no pulse that occurs, so there's no aliasing. But it has some definite disadvantages. And one is that you don't know exactly the location that you're getting the Doppler shift from. So this has become a problem. A lot of women will use continuous wave Dopplers. They can buy a home held model or a home model and use it at home on themselves to detect the baby's heart rate. So one lady, this was a case that came up, she utilized it and she heard the heartbeat. And she went into the doctor the next day and the baby was dead. Well, she said, but I heard the heartbeat. And he said, well, yeah, you might have been listening to your own heartbeat. So she could have been picking up the wrong heartbeat. You don't know with these continuous wave exactly what you're picking up. So that's one disadvantage. That's also known as range ambiguity. Because of the range ambiguity, we don't know, we can't make pictures with continuous waves. So there's no imaging that's done with it. Okay. And there's also no time gain compensation. Now, the advantage of it not only is that it detects high velocities, no aliasing, but it's also very sensitive. So we can use very, very low signals. So our continuous wave transducers, they're very cheap, easy to make, very inexpensive. They have no backing material. They have a very narrow bandwidth, which is good for Doppler. It would be horrible for imaging. They have a very and they have high sensitivity. So they're able to detect very low signals, able to detect very small frequency shifts. With duplex imaging, though, we get the advantage of utilizing a pulsed wave ultrasound, and that gives us the ability to make pictures, and pictures are good. And so we call duplex imaging when we have a grayscale image with a spectral Doppler, grayscale image with spectral Doppler below it. This is dual mode or duplex, okay? So simultaneous anatomical imaging and Doppler. Technically, anytime you have two modes on the screen, it's duplex. So if you have M mode plus a grayscale image, that would be a type of duplex. Doppler plus an image is what we have here, and that's what most people refer to as duplex imaging. But also color Doppler plus grayscale would also be duplex imaging. We don't usually call the M mode or the color Doppler duplex. We do utilize the term duplex for Doppler, spectral Doppler, and an image. So in pulse wave Doppler, this uses pulses like any other pulsed imaging technique. It utilizes a single crystal. It alternates between transmitting and receiving modes, so we know we're very familiar with that now. Only one crystal is needed. It has the advantage of providing us with range specificity, so we know the exact range, the exact location that the signal is coming from. Its biggest disadvantage is at high velocities, it becomes inaccurate due to aliasing. And by now you're probably going, okay, what the heck is aliasing? This has come up like 12 times in the conversation. Well, we'll get there before the chapter's over. Trust me. So pulse wave Doppler, you have a sample volume known as a gate, and the system will then calculate the depth and size of the gate. What the gate does is it tells the system that this is the time we're going to listen to the signal to determine the Doppler shift. This is the only time we want to listen to the signal. Okay, so when that signal comes back from the gate, those echoes are processed. The rest of the echoes that come along this intonation line are not going to be processed. Only when they come from this gate are they even processed. So pulse wave Doppler transducers are capable of both imaging and Doppler analysis. When they are used together, we call them duplex. Characteristics of these transducers is they contain a backing material. They have a very short pulse. That gives us a low quality factor. It gives us a wide bandwidth. And it also, because of the backing material, is lower sensitivity than continuous wave. Now we're going to get into aliasing next. All right, so what is aliasing? Aliasing is the most common error in Doppler ultrasound. This occurs when velocities are incorrectly displayed and it's going in the opposite direction. So you can see we have velocities. There's our baseline in the center of our spectral display with velocities going up and wrapping around and coming into the bottom. This is known as aliasing. Aliasing will only occur with pulse Doppler, never with continuous wave. Aliasing occurs when the sample rate is too low. Your sample rate is your PRF, your pulse repetition frequency. Aliasing occurs when the Doppler shift exceeds the Nyquist limit. And the Nyquist limit is the PRF, the pulse repetition frequency, divided by 2. Another way of saying that is that the Nyquist limit is the highest Doppler shift that can occur without aliasing. Okay, I'm going to try to describe how this pulse repetition frequency and aliasing all work together and why this Nyquist limit exists. All right, so if we have a Doppler frequency, and you can imagine a Doppler frequency like any other sound frequency. It consists of, you could draw it as a sine wave, right? You have some peak compressions and you have rarefaction, if you will. But this is the Doppler frequency. Remember, so we're taking the difference between our transmitted frequency and our received frequency, and we get this Doppler frequency. We're going to call that F Doppler. That is a signal of about a couple thousand hertz, and we obtain it by measuring with our PRF, our pulses. Okay, so now let's look at how we measure something. So each time we send out a pulse, we can measure this sine wave. So if we send out enough pulses, and each pulse is individual, right? So we get a measurement with each pulse, and if we send out enough of them, then we can reconstruct digitally this sine wave. So I'm going to now reconstruct it, and we're going to say, okay, this is what it looks like to the computer, all right? This is what it looks like. We're reconstructing it based on our periodic sampling, and that's what it looks like. And when we look at that, we can go, oh yeah, that sort of looks like what we started with, okay? Not enough detail. Well, if we put in some more detail, of course, then and sample more, then we see that it actually starts looking better. Okay, so now let's connect these dots. We're doing more sampling, and you can see that it starts looking much, much more like the original sine wave that we had, or the original information that we had. Okay, so the more samples we take, the more PRF, pulse repetitions we make, the better we can reconstruct our Doppler. Now let's take an example of, let's say, a Doppler that's not quite enough. Okay, so here we have a PRF where it's not enough. And we're going to sample this Doppler frequency. We're going to sample it every once in a while. Okay, now when we connect those, we see that does not look at all like the original wave. Okay, that's because our sample rate was too low. Okay, so the actual sample rate has to be at least twice um, per wave, per per cycle. Okay, excuse me, per cycle. So at least twice. So we're going to put in 2 per cycle. We're going to go right here, and we see that if we do that, we can recreate our signal at the bare minimum, just like that. And so we can see that in this case we have 1, 2, 3, 4 peaks. And if we look at our actual wave, we have 1, 2, 3, 4 peaks. Okay, so yes, that matches up. That works. Now, if we do that a little bit less, okay, so we sample less frequently. I'll make bigger dots this time. And so if we're going to sample less than twice per wave, I'm trying to make these look even here. Okay. Then we get a sample that doesn't look like the original. Okay, so slightly less than twice. See, and that's aliasing. That's saying that, oh, that's a much lower frequency than it actually was. Okay, so that's aliasing. And so when our PRF, our sample frequency, divided by 2, when that situation occurs, that's called the Nyquist limit. And so when that situation occurs, we are actually sampling just twice each cycle. So at the Nyquist limit, you're sampling twice each cycle. And that's the minimum you can actually sample and get a reconstruction of the waveform that is your Doppler frequency. So the Nyquist limit is the highest Doppler shift that can occur at a given PRF without aliasing. So we have to learn to avoid aliasing. And we can do this two different ways. We can increase our pulse repetition frequency. We can take more samples of our Doppler shift, or we can reduce the frequency of the Doppler shift. Okay, so we can raise the PRF by increasing the Doppler scale, and that's called the scale. On other machines, it's called the PRF, which actually makes more sense. We can adjust that control. We can lower the Doppler shift by reducing the insonation frequency. Remember, our equation allows us to lower the Doppler shift by decreasing our originating frequency, or we can increase the angle of insonation. But remember, we can never increase our angle of insonation above 60 degrees. So we're always going to be limited by that. So that's aliasing. That is the number one thing with Doppler that you have to avoid. So let's talk about sample volume depth and aliasing. Okay. Sometimes when your sample volume depth is too low, then as you know, the deeper you go, the lower your PRF must be, the longer your pulse repetition period must be. And so the slower the PRF must be. So when you go deep with your sample volume, you're going to run into a situation where you're limited by the depth of how high your PRF can be. And in that situation, aliasing is more likely to occur. So we can control aliasing by maximizing the scale, the PRF. And when you say scale, we're talking about the velocity scale. The advantage of this raises the Nyquist limit. The disadvantage of it is that it reduces our sensitivity to low velocities. So aliasing can still persist even with very high velocities, even if we max out our scale. So if we max out our scale, we still may see aliasing if we have a really tight stenosis in our patient. The other thing you can do to reduce aliasing is use a new window with a shallower sample volume. This allows you to increase your PRF even more. The disadvantage, of course, is that this only works when there exists a window that you can scan that's shallower. Other things we can do to control aliasing are select a lower frequency transducer. Okay, this gives us a smaller Doppler shift, which improves aliasing, right? Smaller Doppler shift, and we don't need as high of a pulse repetition frequency. The disadvantage, of course, is that you get decreased image quality sometimes, but the biggest disadvantage is you get a significantly reduced signal from Rayleigh scatterers. Okay, so you don't get as much Rayleigh scattering. Well, the truth is below 3 centimeters, it doesn't matter. The attenuation is so high that reducing the signal, the loss of Rayleigh scatterers doesn't matter because anytime you go deeper than 3 centimeters, you want to reduce your frequency because of attenuation anyhow. Okay, fourth, baseline shift. So baseline shift is just raising that baseline up or down in your imaging. And the fact is that this doesn't actually change aliasing. It changes the the display of it. So it's not really changing the aliasing. It's just changing the display. So our advantage is that it makes the image look better. Our disadvantage is that it may not be enough of a change to make the aliasing go away. Fifth, you can utilize continuous wave Doppler. Advantage, you never get aliasing with continuous wave Doppler. There's a significant disadvantage though, and you get range ambiguity and no picture. In our profession, picture is everything, so that's usually not acceptable in any imaging department. And then lastly, use less of an angle of inclination. The advantage is that this decreases the Doppler shift. It also improves signal strength, but the disadvantage is we can never go above 60 degrees to the blood flow. And so this may not be possible from within our acoustic window. So to summarize the pulse versus continuous wave, this is straight out of the book. I don't think I'm going to read the whole thing to you. Um, so with pulse Doppler, we get pictures. With continuous wave, we get no aliasing. So those are good things. On our spectral display, let's talk about that for a little bit. We haven't discussed the spectral display. The gray shades on the Doppler spectrum are related to the amplitude of the reflected signal. So what that means is that the brighter the pixel in your spectral display, the more blood cells are at that velocity, okay? So the x-axis is always indicating velocity, time. The y-axis is indicating velocity. So when we see a very dark gray pixel, we know that there's not many blood cells that are going that slowly. When we see a bright white pixel, we know that there's a lot of blood cells that are going that quickly. So this is how to read the spectral display. And of course, the height is the velocity. In our color display, velocity information gets superimposed over grayscale anatomic images, and we're able to see pretty pictures. Okay, this uses a different pulsed ultrasound technique than the spectral. It does have range resolution. It has to because we're getting an image. It is subject to aliasing. It's far less angle dependent than spectral displays, and it displays average velocity information, and that's an important point. When we look at our spectral display, this displays instantaneous velocity peak velocity information instantaneously. The color is average velocity information. Okay, so there's a significant difference in those. With color maps, there's two different types of color maps that are available to our display. And what a color map is, it just says that I'm going to use this color for flow towards the transducer. I'm going to use this color for flow away from the transducer. All of them utilize a black band in the middle to indicate no flow or change of direction of flow. Well, anyhow, change of direction, you have to go to 0 at some point to change direction, so that means that's why it's black. The other velocity map is one called the velocity variance scale, and that uses not only that one color for flow towards the transducer with a particular hue indicating the velocity, but also if you go from left to right across the scale, you can see that it changes hue that way also. So the right side of the scale is a hue indicating turbulent flow, and the left side of the scale is a hue indicating laminar flow. So you can put your color on and immediately see if it's laminar or turbulent. This velocity variance map is normally used only for cardiac ultrasound. Okay. We don't use it very much in general or vascular ultrasound. It's utilized in cardiac ultrasound a lot, though. And so this, what you need to know about the velocity variance map is that it exists, and it indicates more variable flow across a particular velocity. Okay. Really, if you see an image with this type of a velocity map on it, the answer is going to be, something like C, velocity variance map. If you see this kind of a scale, this is the normal scale. This is a velocity scale. Okay. Those are really the only questions that you get with those. All right, let's look at flow direction in a sector image. Now, a sector image or a curvilinear image is a little harder to determine flow direction than in a linear array one where you can just drop the angle down. So in a curvilinear image, you examine your color map or your scale to begin with. Okay, you identify which color is coming towards the transducer. And then when you look at your image, if you find that color, you know that it's coming towards the transducer. So this section of red here is going more or less in, let's get a little pen going. There we go. It's more or less going in this direction, right, towards the transducer. Okay, so it must be going, the bottom vessel must be going from right to left. That's towards the transducer, just slightly towards. Okay, so it's not coming directly in this direction. It's just kind of gently going towards the transducer along this path. When we get over here, you can see the velocity is more or less going away from the transducer. Okay. Now, for the vessel above it here, it's a little harder to see, but you can see that the red part is going towards the transducer. But this is almost 90 degrees at all points. The blue is going away from the transducer, and we can see when we get over here, you can see this curving downward of the vessel wall. So the blood is going away from the transducer, and so it is going from left to right. Okay, so we have right to left flow on the bottom, left to right flow on the top. Because it's a continuous vessel, this blood flow over here must be the same direction left to right as the blood flow over here. Now, also on this image, you can see between the red and the blue, you can see this little area of black in there, okay? And also we see it right here. Little areas of black. That means that it's changing direction. It's not meaning that the blood's changing direction. It means it's going from towards the transducer to slightly away from the transducer. Okay, when we talk about change of direction of blood, we're talking about normally the change, is it going towards the transducer or is it going away from the transducer? All right, let's look at the flow direction in a rectangular image, and this is the one I showed you in the lab. What's going on? There we go. All right, so flow direction in a rectangular image. The Edelman book has you draw a picture that comes, a line that comes down from the pointy end at the top of the box, the color box. And then you can look at your scale. Blue is away and red is toward. So if it's blue, it's moving away from that line that you've drawn down. Okay. If it were red, it would be moving towards that line. Okay, whoops. It's like the world's worst drawing tool. So this is blue, so it must be moving away from that line. Therefore, it's moving from right to left. Now we're going to get into color Doppler and how it's made. With color Doppler, we utilize something called a packet in order to create the color Doppler information. And all a packet is extra pulses that are sent out, okay, along the scan line. So if you have more packets, or we call it also an ensemble, packet or ensemble, more packets give you more accurate velocity measurements, again, in color. Fewer packets give you less accurate velocity information, but more packets give you more increased sensitivity to low flow. Okay, and the disadvantage to larger packets is you get a significant decrease in your temporal resolution. So how this works is that normally when we're doing an ultrasound, we send out a pulse, we wait for echoes to come back, and then we send out another pulse. And so this is how it works in grayscale imaging. With color imaging, we send out a pulse, we wait a bit for echoes to come back, and then we send out another pulse, wait for echoes, send out another pulse, and wait for echoes. And these, therefore, is called a packet. So in where we would be sending one pulse in grayscale, we're going to have to send 3 pulses to do a color image. So significant reduction in temporal resolution. And so if we look at that, how it works with, there we go. Each line that is formed in color comes from multiple acoustic lines of information. Okay, so when you turn your packet size up to 24, guess what? You're sending out 24 pulses for each line of your color display. That's a lot of information. All right, power Doppler. Power Doppler is also known as energy Doppler or color angio, and this identifies flow in vessels. However, it doesn't evaluate the direction or the velocity of the flow in the vessel. So we end up with an amplitude of the signal without really getting velocity information on the signal. So as our regular color display showed us the mean velocity, the power Doppler display only shows us flow, and that may not be as useful as we wanted. The advantage of power Doppler is that it has an increased sensitivity to slow flow, such as in small vessels, you can see perfusion easier. It's not as affected by the Doppler angle as other types of imaging. There's no aliasing that occurs with it because there's no velocity information. But of course, the disadvantage is that there's no velocity information. You get lower frame rates, and it's particularly susceptible to an artifact known as a flash artifact. So when you are taking your SPI exam and you see a question that says, what artifact is power Doppler particularly susceptible to? You could answer now, flash artifact, because now you know. So Doppler artifacts are unique artifacts that occur only to Doppler. We get something called ghosting or clutter, and this is low frequency Doppler shift caused by tissue movement or tissue walls. In spectral, it's known as clutter or wall thump. So you can see on the spectral tracing here, we see these very bright echoes here. This is called a wall thump. In color, it's known as ghosting or color bleed. Okay, we can utilize something called a wall filter to eliminate this clutter. This will allow us to reject this signal, this low frequency signal, in our Doppler processing. And so these are known as high-pass filters because high velocity, high frequency information is passed through for processing, and low frequency information is not passed through for processing. So Doppler artifacts such as, oh, we're missing a picture there. Let me see if I can find it.